Okay, welcome everyone. Good morning. I'm excited to introduce Jay Guo and Daisy Guo, both from IBM China, where they are software engineers. Jay is working on the Hyperledger Fabric, and Daisy works on the Knative project. And they're going to talk about using Hyperledger Fabric on Knative and managing the lifecycle of smart contracts on Kubernetes. So I'm pretty excited to hear about that use case. Take it away.
Thank you.
Thank you. Hello, everybody. It's quite interesting that some people are still interested in this very exotic topic. So thank you for coming. I'm Jay. I'm currently a maintainer of Hyperledger Fabric, which the project I will be talking about later. And this is my colleague, Daisy. Today, we will firstly talk a bit about blockchain in general and Hyperledger Fabric, which is a permission blockchain framework. And then we will dive into Fabric transaction flow, so you get a very basic idea like how Fabric works and what kind of role smart contracts play in it. And then we'll talk about the current implementation of smart contract lifecycle and see the flexibility, but also the complexity coming from it and how we plan to solve it. Then we will move to how we actually manage to move that lifecycle management to Tekton plus Knative, and see the actual improvement in terms of simplicity and scalability. And then we will give a very short demo to see like it actually works. And then we will draw a conclusion and lay out some future work. Okay, let's get started. So I'm pretty sure like probably some of you already heard about blockchain or know at least there are like several very popular projects like Bitcoin or Ethereum. But I will just lay the ground, like some background from technical perspective. So blockchain essentially is a distributed system that tolerates Byzantine faults, meaning that you have a network that consists of a bunch of nodes, and some of the nodes may be malicious and they just want to alter the data or trick others to believe in their changes in order to get like a benefit financially. And blockchain is such a network that is autonomous that can manage to tolerate either from like 1/3 or 50% of the malicious nodes, and depending on the different consensus algorithm it's using. And they collectively manage a shared data, which users can have trust in it and can trade with each other, and or can use this kind of mechanism for many other use cases. And then each node will maintain a verifiable, tamper-proof append-only locks, meaning basically that is the chain blocks where the name comes from. And the lock or the ledger is append-only, meaning you can only add new data into it, and you cannot alter the history. So on the chain, we will have the full history of all the transactions, and they are chained together with a hash link. So you cannot really alter one block or some data back in the history and trigger others to believe in it. And thirdly, there are mainly two categories of blockchain frameworks out there today, public or consortium, or we often refer them as permissionless or permissioned. They're really designed for very different use cases. Probably many of you know Bitcoin or Ethereum. They are referred as permissionless blockchain, meaning you can either today, any time, you can just download all the blocks on your computer and start mining. If you get lucky enough, you probably can earn some money today. But nevertheless, you don't really need any permission from anybody to download those data, participate in the consensus algorithm, or start trading with others. You just don't need any permission to do that. But that solves quite a lot of problems and got very popular since the day zero from in the industry. But that doesn't really match many of the industrial use cases, like many organizations or companies, for example, banks or insurance companies or so on and so forth. They are just not very comfortable letting others joining the network and instantly pull all the data available in the network. Even though that data might be encrypted, but still your key might be lost, or there are some other future technologies that can break into it. They just don't feel comfortable letting others know the data and they want to trade privately. Probably you have a network that consisting of, let's say, a limited number of organizations, and they want to just have a common ground or common trust with each other to be able to trade within the network, but they really don't want that data to leak outside of this network. Or if a new organization join the network, they need a very explicit permission to join or to be able to trade with others. And also, they want a finer grain permission. Basically, you can, depending on the access control, you can trade within the network on certain type of transactions, and you're not allowed to see all the data, but only the ones that you're interested or you're allowed to. So this different level of permission, which really is, as we refer as the enterprise blockchain technology. Basically, it's really focusing on solving the problem within the like B2B kind of network. So it's basically, people used to refer like public consortium as in a battle, but I mean, we really don't see that way. We think they are just designed for very different purposes. And a few words about the project. Hyperledger is also a member of Linux Foundation, similar to CNCF or Node.js. It's also, it's founded in 2015, I think, and so it's about to get the 5th anniversary. And it's also an umbrella kind of a model hosting many projects. But all of them have special focus on the enterprise blockchain technologies. And Fabric, which I'm currently working on, is the first graduated project out of this Hyperledger umbrella. And it's Apache 2.0 license. The core of Fabric was written in Go. And as we have several SDKs and smart contract language available in Go, Java, and Node. So all the general purpose languages many developers are probably more familiar with. And it has currently more than 270 members. And I just outlined several premium members. Okay, next we're going to talk about the transaction flow, like exactly how Fabric works today. So first of all, you have a transaction that contains several arguments. For example, we have A, B, and 10, meaning I want to transfer 10 tokens from A to B, and F, which is basically the targeting contract that actually carry out this transaction. Then I send this transaction to the smart contract, which has a very simple logic here. Basically, get the current balance of A and B, and checks if A has enough balance, like let's say in this case it's 10, and then I just deduce that amount from A and increase the balance of B, then mission complete. Very simple. And this smart contract in Fabric, actually it produces a read-write set. Basically, in this case, the output will be, I have a read set is A, 100. Initially, the balance will be 100 at version 1. And B also 100 at version 1. And the write set is basically, I want to write A plus 90 at version 2 and B 110 at version 2. This is the read-write set is basically the output of the smart contract. And then this output is batched into a block. Then the block is disseminated among the network and collect the consensus agreement. And then we call this block final and eventually written into the chain, basically append to the tail of the chain. Then this read-write set is extracted from the block and applied against a local state ledger, basically maintaining the key value of A and B. And then this result will be reflected in this particular node. And every node will do this process individually in parallel, and they will have a correct data maintained locally. And if any node is malicious, it cannot really, let's say if a node manipulates its own local ledger, that would not affect others, and people can still, like by collecting a sufficient amount of results, it can still see, okay, I can basically recognize some node is doing something fishy, and I can still have trust in this whole network. And it's very important that Fabric has a very, I say, opinionated transaction flow comparing to some other frameworks out there. Is basically it reach consensus on the output of the smart contract. But many others like Ethereum or EOS, other blockchain platform, they reach consensus on the input of this smart contract, meaning they firstly agree on the input, basically the transaction, and they individually apply that input, basically feed that input into the smart contract, and then generate exactly the same output. And the smart contract is normally compiled into bytecode, written into the ledger, and whenever it's required to execute, it's just loaded from the ledger, and they have purposely designed virtual machine to execute that smart contract and produce the result. But the Fabric will basically consent on the output of the smart contract, which gives it a lot of flexibility, which I will cover later. And the output basically, as I said, is the read-write set, and the blocks actually contain all these produced results. So to summarize a little bit, smart contract in Fabric or in blockchain in general is programs. They are embedding business logics. Like in this particular example, it could be very simply transferring token from one account to another, or even more simpler, you can just set and get and put a key value. On the left side is a hello world example from Ethereum. It's the program language is called Solidity. It's invented by Ethereum, and they also have set of toolchain to compile and debug that smart contract. On the right side is the Hyperledger Fabric, which is written in Golang, essentially the same logic, and all the smart contracts are deployed on each blockchain node, and they are executed on demand with external input, which is basically the transaction. And so basically, sometimes we rely on the side effect of the smart contract, like like we said in the Ethereum, you execute the smart contract, it alters the ledger, which is the side effect of the function. Or we rely on the return value, basically the transaction output, like in Fabric, we rely on the read-write set, which is the output. And a smart contract are stateless. It doesn't really store any data locally. It alters the global ledger. It's lightweight. Normally, we don't put very complex logic into it for very obvious reason. Like in Ethereum, all the execution of smart contract will cost you money. And you want to really design your smart contract in a way that is financially efficient. And it's ephemeral, meaning it's executed on demand. And after completion, it's run to completion and then terminated. It's never a service that long running or serve any request. And smart contracts are deterministic, meaning we don't allow random number, we don't allow a time, so that with exactly the same input, you will get exactly the same output. Sometimes we have requirement to invoke external APIs, like to query, for example, current stock price or the weather or some sensor data, but that will require very different mechanism. We normally refer as Oracle to make sure that all the different nodes they invoke external API will get exactly the same result. This is again to maintain the determinism. And also smart contract can be composable. You have very tiny smart contracts, and many of them, and they can invoke each other, so you can compose these contracts into a bigger logic. And the smart contract Fabric, we have a certain API to actually update the ledger. This only lists the corrupt ones, and we also have many more for some more complicated logics. And smart contract in Fabric runs as a separate process. This is another very different design decision comparing to other blockchain. Others normally call it on-chain smart contract. Basically, you store the contract code in the ledger, extract it, load into a in-process VM, and get the output. That's normally the on-chain process. It runs within the node process. But in Fabric, the smart contract runs as a separate process. Normally today, we actually run that in a Docker container, which I will talk about later. And it communicates with the Fabric node via a gRPC stream. And then let's talk about the lifecycle of the smart contract today. So firstly, you have a peer, a Fabric peer that's running. And then you install a smart contract on the peer. Basically, what you do is upload the tar. And the peer will extract the content of the tar. Basically, it's Golang or Java code. And that peer relies on a local Docker daemon to compile, to spawn a compiler container, compile the code, and get the output, build that output into a Docker image, store that locally in the registry. And then this installation, you can think of it as a Java class. Basically, when I install a smart contract, I'm creating a class, but that has not been instantiated. It cannot be used because in Fabric, we have this notion of channels to guarantee the data privacy. You have, for example, on a single peer can run a supply chain channel, or a trading channel, or provenance channel, and each channel has its own ledger to keep other nodes in other channels from seeing the data within this channel. So after you install a smart contract, you need to instantiate that contract on one of the channels to be able to use it. And what the peer actually does is to grab that Docker image we just built and start as a Docker container, which again is talking to a local Docker daemon. And the container will initiate or establish a gRPC connection with the peer, which is registering itself. And then users can now invoke the smart contract. Basically, it's sending a transaction to peer, and peer will forward that transaction to the container, and they run a certain protocol to exchange data, to query, or write data. So this model works since the beginning of the Fabric, but it has very clear problems, right? Firstly, or mostly, it talks to a local Docker daemon, which violates quite a bit of security practice. Like in Kubernetes, we shouldn't really manage your own lifecycle of the container. And what we do today, some workaround or terrible hacks are running Docker in Docker in Kubernetes. And secondly, the complexity in managing container is all built into a Fabric peer. Basically, as I said, build image, store the image in the registry, start a container, make sure the container is up and running, restart it when it's crashed, and delete it when we upgrade or delete the smart contract. This is basically all managed by peer, but as you see, Kubernetes does pretty well all this job. And a third one is it's hard to develop and test contract. For example, very often we want to try out a new smart contract. Whenever I deploy, I need to go through the whole life cycle, need to upload tar, wait for it to build, and if something goes wrong, I need to rerun this process again and again, which is quite burdensome. And the fourth one is waste of resource, because let's say you deploy thousands of contracts on one peer. Basically, you have thousands of containers running on the same host as peer, and they are probably idle, doing nothing when there's no transaction coming in, but it's pure waste of the resource. And also, we covered the co-location of peer and contract. They are currently running on the same host. So we definitely want to solve all this problem, and we want to basically offload this lifecycle management to something more awesome or something more dedicated for this job. So we have Tekton and Knative to the rescue. I will hand over to Daisy, my colleague, to cover this part.
Thank you. So let's look at Tekton. So Tekton is a Kubernetes native open source framework for creating CI/CD system. It lets you build, test, and deploy applications to public cloud on-premises system. So there are two major projects in Tekton which help you to trigger a process to build and deploy your app. First is Tekton Pipeline. Tekton Pipeline provides several Kubernetes-style resources for declare CI/CD pipelines. For example, you can define task, which is a collection of steps you would want to run as part of your flow. And the pipeline is a sequence of tasks and parameters and resources used as input and output of the task. And the Tekton trigger it defines some Kubernetes CRD to control, to allow you to extract the information from events payload and feed this payload to a pipeline template and start that pipeline template. So with trigger, you are able to start a pipeline based after some events happen. So with Tekton, we are able to build image on the server side, which is which partially resolves the security issue caused by Docker daemon. Also, with Tekton, we are able to create pipelines to build, deploy, and test the contract source code, which makes them automatic and improves the developer experience. So let's look at Knative. So Knative is a Kubernetes native serverless platform, which defines a set of primitives to build modern source-centric and container-based applications. Knative is Kubernetes native, so it can leverage all the tools in the whole Kubernetes family. It is based on, it is use Kubernetes to do the auto scaling and use service mesh, for example, Istio to define routing and network programming. And it can also use Zipkin or Prometheus to manage the observability. There are two major components in Knative, which is Knative Serving and Knative Eventing. Knative Serving, it defines and controls the serverless workload behaves on cluster. For example, the scale up from 0, or for example, quickly create your service from a source code. And the eventing enables the late binding event source and event consumers. So here is an example of Knative service. The concept of Knative service can be complex, but as a common user, you may only need to understand that the parameter is your image URL. If you have an image URL, you are easily create a Knative service. Knative will manage to create all the artifacts to offer such a service. So there are also some optional parameters such as port and environment. For example, here, because the peer and the contract needs gRPC stream to communicate, so we have to define a H2C port here. There are some characteristics of Knative service which are quite fit to the smart contract. For example, they are both lightweight. They are small tasks. They will terminate for a short time, and their Knative service is containerized and stateless. There is an endpoint for third party to invoke, and the Knative service can scale up to infinity and scale down to 0. And if you are using public cloud to run your Knative service, you can pay by usage. If you are running your premises cloud, many services can share the same hardware, so you can save your resource. And it also, you can easily get the observability and the secured access through mutual TLS. So when we add, after we add Knative, we can delegate the container management and the orchestration to Knative and Kubernetes. Peer doesn't need to manage containers at all, so Peer doesn't depend on Docker daemon. And Knative service can scale down to 0, which is a kind of resource saving. And the peer and the contract is not necessary to locate in the same host. They are completely decoupled. So let's look at what we have done. We propose to use Knative and Tekton to manage the lifecycle and the orchestration of smart contract. We use GitHub to store contract source code. We use Docker Hub to store Docker image. And we use Knative and Kubernetes to run service. When a developer adds a tag to GitHub repo, let's see what will happen.
I want to show the command line, but apparently it doesn't work well with PowerPoint. There you go.
Okay. So let's see. Let's see what will happen. Okay. So I will add a tag. And add a tag to Git. Okay, so you will see the tag has been added. And okay, so the pipeline is running here. So let's see what's the backend. Okay, let's see what happened in the backend. Okay. When user add a tag to the GitHub, the event message will send to event listener, and the listener will trigger a pipeline. There are 2 tasks in the pipeline. The first one is source to image. Source to image will build from your GitHub source code to a Docker image and push the image to GitHub repo. And the second task is to deploy to Knative service. So a Knative service will be created, and an endpoint will be exported. When we have the service and the endpoint ready, our Fabric contract lifecycle will be changed.
All right. So basically, as we said before, we're uploading a tar and building the container, building the code. And now what we do is, from Fabric point of view, we basically stole the idea of build pack. Actually, one of the maintainers was working on build pack back to Cloud Foundry days. And we separate them into detect, build, and run phases, which are invoking external or customized binaries. And you can plug in whatever logic into these phases. And then we alter this build phase, basically saying, OK, just store that URL into locally. And whenever the smart contract is called, we will be just go to this URL and proceed. And the new lifecycle will be, instead of uploading the tar, you will just upload a URL. And the peer doesn't compile, it doesn't build Docker image anymore, it just store that URL locally. And we still need instantiate tool for the Fabric, but the instantiation doesn't really do much in terms of the code building or the image building. Is still on Fabric side, just make sure that the instance of the smart contract is available on the channel. And then the user can now just invoke smart contract if that contract service is running on the Knative. And in the demo, as Daisy already showed, that we just tag the repo, push that to GitHub, and the contract will be automatically extract by Tekton and built into Docker images. And hopefully, the compilation is currently finished. All right, so what it does is it's already compiled, and at the first time, Knative will spawn the container for once, and after a timeout, it will just terminate, and now we happen to see that phase. And I have one Fabric peer running locally on my computer in a container, and I've installed the URL on this peer, but there's no smart contract container running on this peer anymore. So we only see a Fabric peer, and the order is under Fabric component. And then we could just, I have a watch here to observe the pod currently running. We can see there's no contract currently running, which is scaled down to 0. And I can run query, and that will trigger a container being started in the, just a second, being started on Knative. And whenever basically it's already executed on demand, and the container will keep alive for a while, I can now invoke. This is basically saying I want to transfer 10 from A to B. And then if I query again, the A will be 90. OK, that works great, but I think I have a bug in my contract. I can actually put a negative number here and actually get money back from B, which is a bug, definitely. I want to update it. And what I do, I simply update the code. I happen to actually comment out this section. It's basically comparing the input number. It should not be negative, and also A should have sufficient amount of balance, which is critical, of course. And I simply make another commit and say ban evil transaction. I tag it and push. Now it basically repeat the previous process again, just upload the code, and then Tekton will extract the code, build again, and when that process is finished, basically I will have a bug 0 contract up and running, and with basically no complex lifecycle management again. And while waiting for that process to complete, we can take, I think, several questions probably. Oh, just a second. I think I have one more slide to show. Here, we outlined the currently Fabric is on 1.4, which has all these problem we talked before. And on master branch, we already built this build pack concept into it. And now you can, we don't really build the Knative into it, but you can still plug in your binary and still build containers locally, or even just talk to Kubernetes API and start a container for you. And it's quite flexible. And our work is basically make that custom binaries work with Knative and Tekton, and so that is completely offloaded to the framework. And in the future, we might consider to add if you have very complex or heavy, computationally heavy task in smart contract, we want to be able to scale up from 1 to n so that it can handle many more requests. And now we can take questions. And I think we are running out of time.
I think we're just a bit out of time for questions, but please do feel free to come up and ask questions at the end, and maybe you can finish off the demo real quick. I think
if I invoke, it will say evoke transaction. So that. Thank you.